Welcome to our lecture on energy transition. Today is the fifth lecture. We talk about fluctuating renewable energy sources, photovoltaics, direct conversion from sunlight into electricity. Today we'll discuss the principle and the characteristics. Next lecture we switch over to photovoltaic systems. Let's take a look at the principle. Here you see the principle of photovoltaic energy conversion. You have a semiconductor crystal with an internal electrical field. This electrical field transports liberated electrons, which are excited by absorbed photons. And you have contacts and a circuit at the solar cell. And you have here R is our ohmic load. This is our consumer. So this is in very, very short words, the principle of photovoltaics. We go a bit deeper into that. So here you see the transport of the electrons. So we have the photo excitation by the absorbed photons. And if the photon energy is enough, it is able to lift electrons into the conduction band. And then you have the photovoltaic effect. So the electrons can travel through the load back to the valence band. It's not wavelength independent. If you have shorter wavelength, each photon contains more energy and is absorbed in an earlier stage and is able to liberate also more energy. You see here it starts at 400 nanometers. This is our ultraviolet, or just at the border of visible and ultraviolet light. Then it goes at 500 nanometers. We have the blue light, 600 nanometers, green, yellow. And at 700 nanometers we have red color, and after 800 nanometers and higher it's called infrared radiation. And here you see the penetration depth in micrometers in a logarithmic scale. So you see here, if you go beyond 1000 nanometers, that the penetration depth goes to 10 micrometers, and if you go to 1100 nanometers, we have 1000 micrometers or 1 millimeter. The width of our original solar cell is usually smaller than 1 millimeter, so the photon doesn't get absorbed anymore. Here you see a cross-section of a solar cell. So you have here the different doping of the solar cell, N region and P region. And in the middle you have the depletion region where you have this internal electrical field. You see in blue color a wavelength entering at 200 nanometers, so it hardly reaches the depletion region. Optimal is the green light, which just gets absorbed mostly in the depletion region. And if you have 800 nanometers, it almost travels through the silicon, but a large part is getting absorbed, and in this vicinity also you have the highest conversion efficiency of a silicon solar cell. Here you see just again in the middle, zone 2 is the electrical field. You have the photo-induced current, you have volume recombination, the lights get absorbed in this region, and the red line is the penetration depth. Here you have also the function intensity as a function of the depth of the solar cell and the absorption coefficient. Here you see the effective conversion efficiency of a solar cell as a function of wavelength. So as I mentioned, it starts in the vicinity of 300, 400 nanometers, while it gets absorbed very much in the surface. This is not very effective. The photon contains a lot of energy, but it only liberates one electron, so the conversion efficiency is very poor. Best efficiency is in the mid-range or red range, about 800 nanometers. There the energy by the photon is exactly sufficient to liberate an electron. If you go further, the energy is getting too low, and also the absorption is not high enough. Here you see the measured relative spectral efficiency of a solar cell and the corresponding spectra of the sun. So you already mentioned in one of the first lectures, this is the spectrum at different air masses or different times of the day. This is at equator, at equinox, that means the 21st of March or the 21st or 22nd of September. At midday, the sun shines perpendicular and the spectrum has a large bluish part, while if you go towards sunset, for example, at 5:20 p.m., you only have an elevation angle of the sun, gamma S, of 10 degrees or equivalent air mass 5.76. Then the spectrum is shifted more towards red color, towards longer wavelength. The intensity is much less, but spectral-wise it fits much better to the spectral efficiency of a silicon solar cell. This is an amorphous cell, so this is more sensible in the blue region. So usually during midday at this position it converts better. This is a cadmium telluride solar cell. The cadmium telluride solar cell has the highest convergency in the middle wavelength, so in the vicinity of 500 to 700 nanometers. Can combine different kinds of solar cell, so it's called tandem solar cell. For example, here is an amorphous silicon solar cell, which is more sensitive in the blue region, and a microcrystalline or crystalline solar cell, which is more sensitive in the yellow or red region, and they are stacked over each other. It's a series connection of the solar cell, and you can see on the right side, you see the combined spectral efficiency. So the upper cell is more sensitive in the region from 400 to 600 nanometers, while the lower cell in red color is more sensitive in the vicinity from 700 to about 900 nanometers. So we had a problem if you have very extreme illumination with very low or very high wavelength only, then one cell is working very good, but the other cell is blocking due to the lower current in this solar cell. This is the most important curve of solar cells and also of solar modules or even PV generators. This is the IV curve. On the x-axis you have the voltage of your solar cell, and the y-axis is the current. This is not a very modern solar cell, but it's been used some years ago. And you have on the left when the voltage is 0, so you attach a very low ohmic load there, ideally a short circuit. So you have the highest possible current. It's called ISC, short circuit current. And on the other extreme on the right side, current is 0, but the highest voltage, this is an open circuit voltage, VOC. In the middle of those two, there is a specific point called MPP. This is the so-called maximum power point. In this point, the maximum power can be extracted from the solar cell. You see this on the power curve, which is the dotted red line here. You start at the short circuit conditions. You have the maximum current, but no voltage, so power is 0. If you increase the ohmic load, here for example, go to a voltage of 0.1 volts, you still have about 1 amp as current. That means the attached resistance is 0.1 divided by 1 is 0.1 ohms, and you have a power which is also at about 100 milliwatts. You see it here on the right side here, that's the power here, 0.1 watts. If you go further, so you further increase the load here. For example, here if you go up to 0.3 volts, the current is still about 1 amps. It's equivalent to 0.3 ohms. Then your power is also in the vicinity of 0.3 watts and so on. And then you come to a tipping point where the current is going down very much and you have reached the maximum power point. You see it here. It's in the vicinity of 0.42 watts. That's for, you call it, this voltage is VMP, so the voltage in the maximum power point. Also IMP, that's the current in the maximum power point. And as I mentioned already, it's 0.42 watts for this solar cell and this illumination. There's also a thing called form factor, FF. This describes the softness of that characteristics. So if it reminds very much like a rectangular, then the form factor is close to 1. While it's very soft, it's decreasing. And this is a voltage at maximum power point times the current at maximum power point divided by the open circuit voltage times the short circuit current. Here you see, if we go to the lower part, the equivalent circuit of a solar cell. First you have a current source which is triggered by the photon flow here. So you have a double number of photons, you have to double the current and so on. Then you have the diode. This is really your solar cell. This is actually a diode. And if you come to a certain voltage, the diode gets conducting. It's in the vicinity of 0.6 to 0.7 volts. And you can't get any further increase in voltage. That's we saw already at the characteristics. The maximum voltage, if you go back here, was here only 0.6 volts. Further on, you have some parasitic resistances. One in parallel, RP. This is caused by impurities in the material, and so some of the current is not going here through the load, what you want. This is the consumption point. It's lost internally by this RP resistance. Further on, you have non-ideal contacts. It's always, if you go back to the very first picture here you see it's always a compromise between good contacts. So you want to ideally cover the whole solar cell with contacts, but you also want the sunlight to enter your solar cell. So the optimum is in the vicinity of about 4% is contact area. From the backside, it doesn't matter if you don't have a so-called bifacial solar cell. If you have a monofacial cell, so sun is only coming, or illumination is coming just from one side. I mentioned you have a contact area of 4%. Here you can have on the back contact area of 100% as contact. So this contact resistance is symbolized by this RS. So what's the effect of those two resistances? Let's start with the parallel resistor to see here. So the ideal would be infinite, so you don't have any impurities, and you see that this curve, from this point of view, it's a negative current, but usually as a solar engineer, you flip this up, then you come back to this characteristics. But here it's really original from the semiconductor engineers, which see here a negative current. So here you have a quite rectangular, almost rectangular characteristics. That means you have a high form factor. If you decrease that current, so there's more current internally lost by this parasitic resistance, you see that the characteristic gets softer. It still maintains almost the same open circuit voltage and the same current, but the maximum power point is very much reduced, and that means the output power also of your solar cell is very much reduced. On the right side, you see the effect of the contact resistance or series resistance RS. So ideally, this resistance would be 0, so full conduction here. So you see here you would have a solar cell which has a form factor very close to 1. But if the contact resistance increases, it gets softer. Also, it's quite hard to define the maximum power point. Is it here or here? The so-called knee is less pronounced of the characteristics. And in total, you get a reduced power output. The performance parameters of PV output. So this is a current supplied to the load. So you have here I is equal to I0. That's the reverse saturation current of the diode. And then you have a E function, E, and in the exponent you have Q, which is the charge of an electron, times V, that's your voltage, divided by N. N is your ideality factor. For ideal diode is 1. Typically it's 2. And then KT, this is a Boltzmann constant, and T is the absolute temperature of the solar cell, minus 1, minus your generated photocurrent, as you saw already in the equivalent circuit. This is the formula for the open circuit voltage. So you have N times KT divided by Q. These are the same variables. So you see here N for the ideality factor, K for the Boltzmann constant, T for the temperature, Q is still the charge of an electron. Then you have the logarithm of E photon divided by this reverse saturation current I0 plus 1. Then you have the fill factor, as I already mentioned. It's the voltage in maximum power point times the current in maximum power point divided by the open circuit voltage times the short circuit current. You have the efficiency of your solar cell, which is your generated electricity, which is derived from VMP, so the voltage in maximum power point times the current in maximum power point divided by the input power. What's your input power? That's the solar irradiance, e.g. G is for global, so you can convert all types of irradiance, of global irradiance, times A, which is the area. Here you see some characteristics of a solar cell. You have here different illumination levels. We start, the upper one is at 1000 watt per square meter irradiance. This is also the irradiance which is used to determine the output power of a solar module or a solar cell. 1000 watt per square meters. It occurs relatively seldomly in Germany. So most of the time you have irradiance level in the vicinity of 200 to 300 watt per square meter. Anyhow, it's used as a reference, and we have the maximum power point as a red star here, and on the x-axis it's our voltage of the solar cell. If you go to very low irradiance levels, you see that the current is directly proportional to the irradiance level. That's clear. If you have, for example, only half of the photons coming in, you only can generate half of the number of electrons. For the voltage, it stays the same for a large range of irradiance levels, but if you go to very low irradiance levels, then also the voltage goes down. That means also your efficiency is decreased. This is the so-called weak light effect. Here you see the low irradiance performance or weak light effect. You see here we have three types of solar modules here. TF1 means thin film A, TFB means thin film B, and as a reference you have CSI. This means a crystalline silicon, and they are normalized to the performance at 1000 watt per square meter here on the right side here. And if you go to lower irradiance level, for example to 200 watt per square meter, you see here that one is performing quite well. The other one, the crystalline, also the losses are minimal, but for the thin film technology B, the losses are quite significant. So it's in the vicinity of minus 15, minus 17% less. This is also some impact on the energy yield of a solar module, because you don't have a constant irradiance. It changes from morning to evening and through the seasons. And if you install such a system in Berlin, for example, as I mentioned already, Germany is only on a longer part of irradiance levels, then this can play a significant role. So you would have a 15% lower energy yield in Berlin. While if you go to Seville, the sun is shining at higher irradiance levels there, and so here, if you see here, the difference is much less, and you would only have a loss in the vicinity of 8% for Seville, Spain, as you saw the table when we discussed irradiance. Let's come to another effect, the effect on temperature on the IV characteristics. So you see here that at increased temperature, the first effect is the current is a little bit increased, because the thermal excitation helps a bit to liberate electrons, and therefore the current is slightly increased. That means also that the spectral efficiency is a little bit shifted towards red or infrared, because you need less energy to liberate the electrons. So photons which couldn't liberate electrons in cold solar cells could do this in a hot solar cell, and therefore you see a quite minor increase in current. But the main effect you see on the x-axis is the reduction in voltage. It's about in the vicinity of crystalline solar cells, minus 0.4 to minus 0.5% per Kelvin temperature increase. So if you increase the temperature by 10 degrees, you have about a 5% voltage loss and also corresponding power loss. The increase in current plays a very minor role. So you see here, we have a standard test conditions, STC called. This is all measured at an operating temperature of the solar cell of 25 degrees. This is usually measured also in a lab, but it's not really realistic. If you have really that high irradiance level, as I mentioned before, about 1000 watt per square meter, you have usually temperature in the vicinity of 50 to 60 degrees Celsius. Here you see the reference irradiance level 1000 watt per square meter and the reference spectrum AM 1.5. As I mentioned before, this is very important because if you have a spectrum which is more reddish or more bluish, it may change the characteristics. Here are the temperature coefficient for several photovoltaic technologies. So here what we saw, the characteristics before had been a multicrystalline solar cell, so module efficiency of 11.8%. Nowadays they are usually much higher. And the temperature coefficient for the power output was minus 0.44% per Kelvin, negative. If you go to the current, you have a positive temperature coefficient, but it's only 0.05% per Kelvin. Voltage, as I mentioned, is the same vicinity as the power loss. It's a minus 0.39% per Kelvin. There's also slight loss in the form factor, so the solar cell characteristic gets a little bit softer. Then you have here a number for the NOCT. This means nominal operating cell temperature. So this is not the standard 25 degrees. This is actual temperature of the solar cell which actually develops. I will give you the exact methods soon. First, let's go to the standard test conditions. Usually used if you buy solar modules, these are usually all measured at standard test conditions. That means that you have cell temperature of 25 degrees, not ambient temperature, but cell temperature. And as I mentioned already, a global irradiance level of 1000 watt per square meter and a spectrum equivalent to air mass 1.5. The angle of incidence of irradiance is 0 degrees, so it's perpendicular irradiance on the surface of the modules. Usually that values are measured in a laboratory or in a factory by a so-called flasher or solar simulator. The index P at the power, for example, if you have V index P, indicates that the power is given according to the standard test conditions. Then I mentioned already the NOCT, the nominal operating cell temperature. This is the actual cell temperature, not the fixed 25 degrees. So in order to achieve that value, you put the solar module in a fixed environment with an ambient temperature of 20 degrees Celsius, a wind speed of 1 meter per second, an irradiance level of 800 watt per square meter only, and the elevation angle of the modules is 45 degrees, so gamma M, also gamma is for M module, elevation angle 45 degrees. And then you measure the actual temperature inside your solar cell. This is an NOCT value. As you saw in the table before, this was here in the vicinity 45 to 50 degrees. It also depends on the conversion efficiency. If the conversion efficiency is quite high, then little heat flow remains, and so interestingly, the temperature decreases at a high performance module. This NOCT is more realistic than the STC conditions, but unfortunately industry doesn't take this because the values are much lower, as you see already by the irradiance level. So you have at least 20% less performance and power output. So the industry always prefers the STC conditions. If you measure the NOCT outdoors, which is very often the case, often don't have these exact temperature values, exactly 20 degrees Celsius, exactly 1 meter per second of wind speed and the irradiance level. And so this is a kind of compensation sheet or compensation graph. So you see here if you have higher or lower outdoor temperature and higher or lower wind speed, you can use such compensation sheets to get the real NOCT. The actual operation temperature also depends on the type of mounting. For example, if you have a free field rack mounting, the temperature is lower because there is convection on the front and the back side. So it's typically 3 degrees lower than this NOCT value. If you direct mount your solar modules on the roof without permitting any backside convection, you have usually an 18% higher temperature as the NOCT suggests. If you, what's most often the case, if you install the module at a certain distance of the roof, if you use a very low distance, for example 2.5 centimeters, an increased temperature is 11 degrees. If you have a standoff of 15 centimeters, then the temperature is 1 degree lower than the NOCT. Here you see the achieved conversion efficiencies of different laboratories. So you see here that the very best solar cells, they achieve conversion efficiency much more than 40%. But this is not standard test conditions. These are concentrator solar cells, so the light is concentrated, or sometimes the spectrum is even differing from air mass 1.5. Here you see it a bit more in detail from the Fraunhofer Institute. So you see here the highest conversion efficiency of 14.1% have been achieved by 4-5 multi-junction concentrator solar cells. This is not relevant for us. So usually what is interesting and are largely available and at an affordable price are multicrystalline silicon or maybe monocrystalline silicon. And there you are in the vicinity of 25-26% of conversion efficiency. If you want to have the maximum cost-benefit ratio, you end up in the vicinity of 19-20% of conversion efficiency. Here you see also some thin film technologies, CIGS and cadmium telluride. There has been some significant improvement during the last year, but the price of the crystalline silicon decreased very much and it's quite stable, while you can say that for the thin film technologies. So the manufacturers are a bit afraid of giving warranty, same as the crystalline silicon manufacturer. That means in the vicinity of 20, nowadays even up to 30 years. Manufacturer and solar cell, there should be a short movie. So you have the sawn wafers here from a multicrystalline solar cell. So here's the diffusion of phosphorus in order to achieve the N region. This is now the anti-reflection coating. Nowadays use silicon nitride to do that. Then you apply the front and the back contacts by screen printing. Then the solar cells get tested by a solar simulator, standard test conditions, 1000 watt per square meter of flash, and you measure the IV curves and you sort the solar cells according to their short circuit current, because in the modules they are installed all in series connection, and the solar cell with the lowest current is determining the entire performance. So the next step now, so we saw how a solar cell is fabricated. Then you interconnect the different cells into a string to increase the voltage, which was quite low, as we know. Just a solar cell is in the vicinity of 0.6 volts, but with 0.6 volts is practically unusable. So increase the voltage to 42 volts in the string and solar module. Formerly, the solar modules had a power of in the vicinity of 50 watts, and nowadays they go up to 440 watts. If you want more power, you interconnect the solar modules in series connection up to the maximum permitted voltage, which was formerly 600 volts, nowadays it's 1000 volts. But the very latest solar modules, they even can be interconnected up to a voltage of 1500 or even 2000 volts. To get a PV generator. If you want to still increase the power, you interconnect these strings of solar modules in parallel. So here you see the interconnection. You have here the thin copper flat wires to interconnect. You see here a cross section of the solar module. Here you have the interconnected solar cells. Then you have a backsheet foil. In between there is an encapsulant called EVA. That means ethylene vinyl acetate. On the top of that is also an EVA layer, and then you have the glass, and then it gets laminated in a so-called laminator at a temperature in the vicinity of 156 degrees Celsius for 20 minutes. And then you connect the terminal here and the frame, and then you do the testing to find out the total IV characteristics of a solar module with the interconnected cells. Here you see the effect of the interconnections. So the very first, the one with a circle here, is the IV characteristics of a cell, what you saw before, the blue curve here. But here you see that the voltage, this is very much compressed. So you have here 0.6 volts is only here. And if you interconnect 36 cells, you have that dashed pointed curve here. The voltage is increasing, the current stays the same. You see it again, the cross section of a solar module. Here you see also kind of cross section at the edge. You have here some sealing and the framing. Sealing is quite important because you want to avoid that humidity gets inside the solar module. This is usually determining its lifetime, not the solar cell. It works virtually forever. But when the module is getting delaminated by humidity, then the end of the lifetime is quite near. The backsheet is usually a Tetla polyester foil, but also there are solar modules which have a sheet of glass on the backside. Here you see some examples of solar modules. On the left side, SC silicon means single crystalline silicon. On the right side, you see a MC, that means multicrystalline silicon modules. In the middle of those two, you see the data sheet of those. So also, as I mentioned before, the power under standard test conditions, open circuit voltage, short circuit voltage in the maximum power point and current in the maximum power point. Here you see a thin film technology on the left, amorphous silicon. On the right you see cadmium telluride. See the problem if you interconnect cells with a different current, or if artificially one cell is shaded, for example by a leaf that is on your solar module and shades one single cell. In this example we choose a shading by 75%. So you have a big leaf here on a cell. Only 25% of its original current is reached, and this causes now a problem because the other cells still have the maximum, or theoretically have the maximum current, but they all interconnected in series. So the worst cell determines the overall performance of those. So you have to make a superposition of those curves, and we take a sample point as an example here. We do a superposition, so we add the same current, because through the module in series connection it could be only one current, and you come to this point with the 3 with the black circle. And if you do it for all points, you end up at this red line as your final IV characteristic of your entire PV module. You see the power is drastically reduced. While 35 cells are working at full power, only one cell is handicapped by a leaf, for example. How to overcome this? So-called bypass diode. So you interconnect a diode in parallel to each cell. Theoretically, in practice, use the bypass diodes over a string or several strings, but ideally would be over every cell. And here we have it on the middle cell. We have handicapped cell by a leaf that's on the cell, and the current is reduced through that. Theoretically, if there's no leaf, each cell has the same current, and you have the addition of the voltages. So you have at cell 1 plus minus, at cell 2 plus minus, cell 3 here also plus minus, and they all add up. What happens if you have the shadowing here? If you have 100% shadowing, the current here through would be almost zero. So it acts like open circuit here, and you would have here a reverse voltage at this solar cell, because you have here plus minus from the upper solar cells and here plus minus from the lower solar cells, so plus here, minus here. That means you have a reverse voltage at these solar cells if the current gets very low or close to zero. That means if you install a bypass diode in this direction, it wouldn't harm the solar cell if it's full power is there, then with plus minus, it would be in blocking conditions, but it will be in conduction position if you have a reverse voltage. What happens if some significant shadows occur? So the bypass diode works in that case, and the current can flow through the bypass diode. Sure, you use the voltage of that solar cell, but still the current is being maintained. You see such bypass diode, as I mentioned, ideally would be a bypass diode over every cell, but usually you use it over 1 or 2 strings and install the bypass diode in the terminal box of the solar modules. In this case, for example, you see here 3 bypass diodes for a module with 6 strings. Next step is to connect the modules to the environment or to other modules. Formerly there was a terminal block and you used a screwdriver to interconnect them. This took a lot of time, and also you have to think that always if there's light, there's voltage on the PV module, and it could be quite harmful if you're working with higher voltages. As I mentioned, if you interconnect many solar modules in series, the voltage could go up to 1000, even 1500 volts. Therefore, nowadays exclusively such interconnectors are used, very often by the company Multicontact or Stäubli nowadays, and the present standard is the MC4. It's a almost non-reversible connection, so you almost have to have a tool in order to disconnect them, but usually if you once connected the module and install them, it stays there for 25 years. Installation could be done very safe and rapidly by these interconnectors. You see such a power plant consisting of 4 strings with several modules. In order to avoid that the current goes from one string into another string, which has a lower current or lower voltage, you use string diodes, which are used as a valve, so they only let current go out of the module string and not inside the module string. It could happen, for example, if you have a lot of leaves on solar modules and the bypass diodes are acting, so the voltage would be significantly lower of one string, and there could be the problem that current would go into the strings. If the solar modules and the cells are equally illuminated, the string diodes are not necessary. Nowadays, for cost reasons, mostly fuses are used and not anymore string diodes, because you have to remember you have this diode and you always have a breakthrough voltage of a diode here, which you have to consider in your losses. Performance ratio. This is taking into account all the loss factors, for example, non-perpendicular irradiance or reflection on the module surfaces, spectral mismatch. You saw this before when we saw the matching of the irradiance spectrum to the spectral efficiency of a solar cell. The weak light effect, as I already mentioned, this is related to the parasitic parallel resistor, the purity of a semiconductor, and also from the fabrication of a solar cells. This is sometimes insufficient edge insulation, and there this is the same effect as impurities in material. Elevated operation temperature. This is related to the mountain type, the ambient temperature and wind and so on, as you saw before when we discussed about the NOCT. This is a performance ratio, so you have the energy output of photovoltaics divided by the irradiance value times the nominal at standard test conditions conversion efficiency. So you have here the conversion efficiency, which is the power output under standard test conditions divided by the irradiance under standard test conditions. That's exactly 1000 watt per square meter times the area of the module. These are already set here, just a repetition. Usually this performance ratio is in the vicinity in Europe at 0.8, 0.9. If you go to warmer climates, then these loss factors are a little bit increased, and so you have sometimes below 0.8 as performance ratio. Come to the market side a little bit. So the cost of photovoltaic technology decreased a lot, while you had to pay about $20–30 per watt for photovoltaic generators. That means 20 to 30,000 euro for a 1 kilowatt PV generator. Nowadays, it's in the vicinity of almost 20 cents per watt, or 2,000 euro for 1 kilowatt generator. That means that the cost drastically decreased by almost a factor of 100. So nowadays, if you have a 1 kilowatt generator and you have costs of 0.2 euro per watt, that means you only pay about 200 euro for 1 kilowatt generator. Not installed generator, but the modules costs went as low as that. On the x-axis, you have also logarithmic scaling. This is the cumulative production. You see here that a price reduction of 25% occurs for each doubling of the installed capacity. So if you quickly ramp up production, as Germany did in the early 2000 years, then there's a significant price reduction. You see here, for example, if you go from the year 2000, 2010, 2015, you see that production drastically increased, and so did also the price reduction. There's some impact also on the installation types. So while even in the year 2006, 71% of the costs of a PV installation had been the modules and only 29% the so-called BOS, balance of systems costs, including the inverter. Nowadays, 61% are balance of systems costs. So the installation, the inverter, the framing of the cables, wiring and installation are higher than the actual module costs, in the vicinity of 61%, while the modules of a small PV power plant, we have to admit, from 10 to 100 kilowatts installed on a roof, are only 39%. This is quite interesting. So this is a study from the year 2000 by Mr. Hoffmann, 900 full load hours in Germany, because you have the standard test conditions, 1000 watt per square meter. If you take a look how much is irradiance, which is in the vicinity of 900 kilowatt hours per square meter per year, That means you have about 900 full load hours for your PV generators, and this led to costs about 60 euro cent per kilowatt hour. If you go further south, for example to Portugal or to Northern Africa, you have 1,800 hours per year of full load hours. That's equivalent also to the number of kilowatt hours per year. There, cost is only half because you have double the irradiance. And the expectation was that in the year 2020, the costs would go down to about 21 cent per kilowatt hour in Europe and to about 10 cent per kilowatt hour here, if you take a look in the southern hemisphere. But the progress, astonishingly, has been much faster. Already in the year 2010, costs has been lower than expected. So in 2015, even more. So even in Europe, costs went down already in the year 2015 to 10 cents per kilowatt hour. If you go further south, costs reach about 6 cents per kilowatt hour. So that's not only grid parity, this is the cost of the peak load grid here. It was below that, it's almost base load costs of electricity. Nowadays, we're even further. In the year 2020, we have for the latest tender about 4 cents per kilowatt hour in the Emirates. Latest tenders showed a cost of 1.5 euro cent per kilowatt hour. So that is base load parity. Here an overview of the feed-in tariff, because in the beginning the cost of photovoltaic energy generation has been much higher than the grid electricity, and in order to accelerate the use of photovoltaics, the German government decided that there is a surplus or a primary tariff for investors in photovoltaic technologies, and they gave you an extra price. So here the photovoltaic price was more than double than the photovoltaic FET, means feed-in tariff. Industry even more extreme. They had EBX spot price. This is a price on the European Energy Exchange, has been much lower than that. This changed in the year about 2010. Then first time the photovoltaic feed-in tariff and the photovoltaic energy generation costs have been as low or even lower than the household price. So it would make more sense to consume this electricity generated by your PV generator on your own rather than to feed into the grid. Because if you go, for example, to the year 2014, you saw that you paid about 30 cents per kilowatt hour for your household electricity, and if you fed into the grid, you only get about 10 cents per kilowatt hour. If you could substitute your household electricity, you saved 30 cents at cost of 10 cents, so you made a profit of about 20 cents, and this is still nowadays the case. So many people are buying batteries or try to adapt their consumption points, for example, by charging your electric cars to the availability of solar electricity from your own roof. This shows a levelized cost of electricity versus a feed-in tariff. So on the x-axis you have your plant price in euro per watt peak. Usually you are on the lower part nowadays here, so in the vicinity of 0.9 to 1. And on the y-axis you have the levelized cost of electricity, cents per kilowatt hour, and the different lines show the different irradiance level in Germany. So if you have the gray line, that's equivalent to Paderborn with an annual irradiance level of 950 kilowatt hours per square meter per year. The red line is Freiburg, the irradiance level of 1160 kilowatt hours per square meter per year. Let's take a look first at Paderborn here. So if you install it, quite expensive in Paderborn for costs of 1.6 euro per watt or 1,600 euro per kilowatt, your generation costs are in the vicinity of 14 cents per kilowatt hour. If you only get a feed-in tariff of 10 cents per kilowatt hour or even 9 cents per kilowatt hour, then it's not profitable at all. In order to break even, for example, here, if you have the remuneration tariff for ground-mounted system here, you have to have at least costs of 1 euro per watt or below that in order to make a profit. It's more easy if you go to Freiburg, for example. Here you see the red line. Even if you have a high installation costs here, it means installation plus the material, it means plus including the modules and inverter, BOS costs and so on, you would have generation costs in the vicinity of 11 cents per kilowatt hour. If you achieve €1 per watt installation costs, you will have generation costs in the vicinity of 7 cents per kilowatt hour. Then you make some profit here, depending whether you have here it is a remuneration for ground mounted systems, or here the upper line is for small roofs. And if you have costs like this here in the vicinity of 7 cents, but you get 12.5 cents, it's quite profitable still today to install small photovoltaic systems. Even more profitable would be, as I mentioned already, while you pay about 30 cents per kilowatt hour for electricity from the grid as household tariff, then it even makes more sense. These are large-scale power plants. These are negotiated in so-called PPA, power purchase agreements, and this has been the development of the value of power purchase agreements. The blue dots are wind power plants, the yellow dots are photovoltaic power plants. If you go back to the year 2012, the cheapest here was in South Africa with a little bit less than 8 cents per kilowatt hour. Photovoltaic was quite high, above 10 cents per kilowatt hour. And if you go, for example, to the year 2015, you see that the best tenders have been in the US, for example, at about 4 cents per kilowatt hour for wind power. And for photovoltaics, it's been in the vicinity still of 12 cents per kilowatt hour. And you see the latest development here, 2016, in the Emirates, you achieved in the vicinity of about 2 cents per kilowatt hour. This been from 2018. You see that the lowest tenders in India for photovoltaic power had been in the vicinity of 1.86 cents per kilowatt hour. If you go to the year 2019, there was a Portuguese auction bid for 1.48 euro cent per kilowatt hour. Sometimes you hear in the discussions, yes, you need a lot of energy to produce modules, and so the effect for carbon dioxide reduction is very low. Yes, this was true in the 80s and 70s because the production of the solar cell was quite expensive and you need a lot of materials. But nowadays production have been very much optimized. You see here the so-called energy payback time. So that means how many years you have to put your modules into the sun to get back the energy you needed for its manufacturing. For Europe, this depends sure on the irradiance value, the EBT, so that's the energy payback time. If you go here to Central Europe, we have in the vicinity of 1.3 years you need to put your solar modules into the sun to get back the energy. If you go to southern Spain, for example, to Seville, it's in the vicinity of 1 year only. To consider, you have a lifetime of 20, nowadays even more, 25, 30 years. So you need only 1 year, a small portion of your expected lifetime to recover the energy needed for production. Correspondingly, also the CO2 emissions for the generation of 1 kilowatt hour of photovoltaic electricity also decreased considerably, as you see here on the right part. So here we are below 50 grams of carbon dioxide per kilowatt hour of electricity. Remember, we discussed coal power plants. This were in the vicinity of 1,000 grams per kilowatt hour of electricity. Even modern hard coal power plants are still in the vicinity of 800-900 grams per kilowatt hour of electricity. Lignite power plants are even worse. They go up to 1,150 grams per kilowatt hour of electricity. Gas power plants are in the vicinity of about 500 grams per kilowatt hour of electricity, so 10 times worse than photovoltaics. There's a world map on that. So as I mentioned already, so in the vicinity 1.3 years in Central Europe. If you go to Northern Africa, about 1 year. If you go here to Egypt, it's even 0.67 years. This is due to the low grid efficiency there. So if you compare photovoltaic local production compared to the local grid there, which is sometimes quite unreliable and related to many losses, then the advantage is even better for photovoltaics. And this is considered in these maps here. So you are many countries, you are well below 1 year of energy payback time. The development of worldwide photovoltaics you see here. So we have a total installed power of more than half a terawatt. It's exactly 633.7 gigawatt in the year 2019. Most of it is installed nowadays in China, but Europe has a big share in it. If you take a look at the latest installation numbers, here you see that in the year 2000, 2011, Europe had most of the world markets has been in Europe, basically Germany, then Spain, then Italy. China exported modules only, but didn't install in their own country. This changed totally. Now worldwide solar modules are produced in China, but also installed in China. Also, the Americas increased a lot, while in the year 2011, for example, the share has been quite minor. The cost decreased a lot. This is the cost development of different energy technologies. So you have here solar, which has been quite expensive. Still in the year 2009, it was in the vicinity of $350 per megawatt hour. This is about 35 cents per kilowatt hour, and nowadays we are in the vicinity of $40 per megawatt hour. It's about 4 cents per kilowatt hour. And if you see some other technologies, for example here nuclear and light gray, cost even increased here and are more than double now than of solar production. Also wind power decreased, but not as much as photovoltaics. They are in the same vicinity of photovoltaic power generation. So coal is now even more expensive, even not considering the carbon costs here. Only problem as photovoltaic energy, you should consume the energy when it's available. Otherwise you have to add the storage costs. They almost double the cost of the photovoltaic generation, but we come to that in a separate chapter. The top countries, as I mentioned already, China, this is 2018 and 2019, followed by the US, India, Japan, Vietnam. Fortunately, Germany doesn't play such a big role anymore. It has been in the 2005, 2010. It's about here vicinity of 4 gigawatt per year what's installed in Germany. Here are the relative market shares. As I mentioned already, in the year 2012, Europe played the dominating role, while nowadays not anymore. It's only about a share of 20% of the global world market on photovoltaics. Yes, there were a lot of complaints about that photovoltaics makes electricity so expensive. Yes, it was true about 10-15 years ago, but nowadays each additional gigawatt of installed photovoltaics only at a price of 0.018 cents per kilowatt hour now, so it's just almost not perceivable anymore. Let's take a look at the influence of a load curve of electricity. So you have here a typical load curve over one day. So formerly this was a traditional load curve. You have some base load, and during midday you added some other power plants. Then only during the midday hours there was a peak power plant which were only used twice a day, at midday and in the evening. These have been quite flexible power plants, for example gas power plants, which were quite costly also due to the reduced full load hours. While the electricity consumption has been adapted to this very cheap baseload power plants, even the households get some price reduction if they consume energy during nighttime in order to keep the baseload power plants working full load during 24 hours. Now we have the influence of the photovoltaics. For example, here you have a gray day. This is the gray part here, and you have a very clear day. This is the yellow part. This will be taken off the load curve, and you see here that these originally quite profitable power plants during midday, or expensive power plants during midday, are completely switched off. You don't need anymore for clear days. And here you see some examples. This was from this year, from the 22nd to 29th of June. You see here the black line is the consumption, and you see here you have an overproduction during the midday hours by photovoltaics. So we have a large share of photovoltaics And this is the lignite power plants. The red is a nuclear power plants. The problem is we do not have a lot of power plants which are really adaptive to this. So at the midday hour for 2 or 3 hours, we have a total overproduction. We produce much more than the consumption, and the energy had to be exported to neighbors for kind of dumping price. That's very unfortunate. It would be better if we would distribute the production more evenly. For example, if you would direct the photovoltaics modules more in western direction. If you see here, western, that means that in the evening there would be more power, a bit less in the midday. And then we could also fulfill the electricity also in the evening hours by photovoltaic energy. In total, the average renewable energy share during that week has been 50.1%. This is about the value what we have all over the year. In the year 2020, probably it's not over yet, but quite probably will be in the vicinity of 50% renewable share. Winter more wind power, in summer more solar power. Let's take a look at the extreme of this week, week 26. So we have here the maximum and minimum operation conditions here. So we have here pumped hydro storage consumption the maximum was 0, consumption was minus 4.71. So this was used when we had the overproduction. So you see here for the 28th at around midday, a little bit afternoon here, this energy has been taken up by some pumped hydro storage power plant. Also import balance, this was also in the same vicinity, so we have negative import, that means export, so we sent about 8.67 gigawatt to our neighbors. We imported about 9 gigawatt in the morning of the 26th of June, and here you have the other power plants. What you see here, that the nuclear power plants are not really flexible, so even the minimum was 4.27 gigawatts and the maximum 5.3 gigawatts. So there was not a big amplitude in that. This is by the construction of these power plants. You only can throttle down to a minimum of 40%. So these are not really adaptive. Even the coal power plants are better. The brown coal power plant, they had a minimum power of 5.45 gigawatt and maximum power of about 12 gigawatt. And hard coal even more, so by a factor of 3. So you have a minimum power of 1 gigawatt and a maximum power of 1.67 gigawatt. Same applies here for oil and gas. Here, gas is almost by a factor of 6.7. Minimum power of 1.7 gigawatt, maximum power of 10 gigawatt. This is a pumped storage, so this is the reverse of the pumped storage consumption. Wind power, sure, there was a lot of fluctuation. Minimum was 1.25 gigawatt, maximum was 19 gigawatt. So this fluctuation has to be compensated by the remaining power plants, and it's hardly possible by nuclear power plants. Also, the flexibility of brown coal is there, but not sufficient. Solar, sure, in the nighttime there is 0 production of photovoltaic power plants, and the maximum occurred around midday, still summertime, so it's 1:30 p.m. That's equivalent to the original time about 12:30, and there the power has been 35.1 gigawatt. So we take a look at this number. So this has been one of the largest, it has been the largest producer. So the maximum of the coal power plant not even reached half of that power what the photovoltaic power plants gave during that week. The load maximum has been at 64.84 gigawatt. This quite nicely corresponds to the maximum of the photovoltaic output, so around midday, and the minimum, so reduced by a factor of 2 before sunrise at 5:15. So the maximum of the renewable share has been 78% and the minimum 27.3%. It was never 0% because they complement each other, wind and solar and biomass. So the minimum has not been 0%. As some people suggest, there is no power available. So here the minimum was only 27.3%. If you talk about costs, it's not only costs about electricity. This shows the principle how costs are calculated, because some people always ask me, well, how are the costs of a solar cell? And they not depend only on the engineering costs or on the production costs, but they also depend on the cost of the raw materials. The cost of the raw material depend on the manufacturing capacity and the availability on the market and the demand. You see here just this so-called merit order principle. It's used at the electricity market also. You see here you have on the very left side on the x-axis, you have the cheapest manufacturer of polysilicon, which is able to manufacture silicon below $10 per kilogram. And if you have a demand of only 20,000 tons per year, the market price for this year would be in that vicinity. If you would have a demand of 100,000 tons, then these factories are not sufficient. You have to add another not so cheap manufacturer, and then price goes up and so on. And this is an example for 2016. So global demand was 67 to 72 gigawatt. And this was here the final price. So this is average price, but the most expensive prices have been above $15 per ton. Here, Wacker, Tennessee didn't sell anything because it was too expensive. Only this company sold their entire stock here, or the entire production capacity in polysilicon production. Same for the production of a solar module. This is not done with merit order, but this shows the components of the costs of a solar module, not solar cells only. Cell is only a part of it. So you have here what we discussed before. If you go to the extra polysilicon, this was the price we got here. And this is a share for one module. Then you have the manufacturing from polysilicon to the wafer, which is more than the raw material cost of the polysilicon. Then from the wafer to the cell. Then you interconnect the cell to a module. This is the most expensive part. And at the end, you end up at about 35 cents per watt for your module in-house cost without any profit. Then this is, if you would outsource this, it would be even more expensive. So this doesn't make sense in this business model if you would outsource that, because then you wouldn't add a cost of a PV module of 47 cents per watt. This is another calculation. So if you achieve cheaper suppliers, you are able then to lower the price to 40 cents per watt instead of 47 cents per watt. As I mentioned already, the actual numbers are extremely valuable and they're not for free. I just wanted to show you the principle, how this is done. Thank you very much.